So maybe from the last screencast, you're like, hey, wait a second, Dr. Pierce. You have been given these generalizations about protons that are attached to the same carbon as being in the same chemical environment. Well, I remember way back when we talked about things being axial and equatorial, that those aren't exactly in the same chemical environment. That's why there's a greater stability when things are in the equatorial position because there's more space. Well, you're right. If we look at cyclohexane, the two hydrogens are in different environments. They're axial and equatorial. But we still only get one peak. Even though these things go through ring flips, right? We still only get one peak in the NMR spectra. And the reason is because a chair flip happens pretty quickly. So it's about 10 to the negative fifth seconds. To acquire an NMR spectra, that takes approximately 1 second. So the different environments of the interchanging protons in the cyclohexane are going to be blurred. You just can't see it because they happen much faster than what it takes for us to acquire a spectra. And so it's analogous to if you have a camera that blurs when objects move too quickly. So in an NMR spectra, basically a peak just reflects the average proton environment of each proton during its chair flip. Now, at low temperatures though, where this process becomes slower, these two signals can be observed. Now, this phenomenon isn't just limited to cyclohexane. If protons in different chemical environments interchange rapidly, then they do give rise to the same NMR signal that reflects the average of those two environments. So let's look at another example. Another example is acetic acid, which is commonly known as vinegar. Its protons are going to, we only get two signals, okay? Because when we look at this, we say, hey, look, CH3, C double bond O, OH. And I've told you the shortcut, unless you've got something crazy happening with a double bond and something that's very, very electronegative, is we can say, look, these three things are going to be in the same chemical environment, and that's going to be in a different chemical environment. Well, in reality, when these spread out in the 3D structure, this proton is closer to this oxygen, and so it's in a different environment than, say, either of these two protons. But they interchange so rapidly. There's so much spinning here that with the rotation here, because remember way back when we did, we looked at the rotation of bonds and we know that these can spin around a single bond. These protons rotate faster than what we can observe in an NMR spectra. So they come out to be chemically equivalent. So for us, again, we can continue to say, look, those are attached to the same carbon. They're going to be chemically equivalent. Now, the beautiful thing about this is we do get some characteristic chemical shifts with these compounds. So when we look at this, the first thing you're going to see here is TMS is at 0, okay? Now, when we look here, this is an sp3 carbon, and so this is a hydrogen on an sp3 carbon. That chemical shift is right around 0.9. This is an sp2 carbon, and with this sp2 carbon, we're going to see right about 1.3. And then this is an sp3 carbon, and a hydrogen on an sp3 carbon, we're going to see right around 0.4. So you can distinguish whether a proton is on an sp3, sp2, or sp carbon based on where the chemical shift is in the NMR spectrum. So if we look at a proton that's next to a CH2 next to a double bond, we'll notice that that chemical shift is 1.7. Notice here, right, we have a ketone, and this is a CH3 next to a ketone, but what we're really looking at here are the protons in red. This proton is going to be at 2.1. Here's a proton next to an aryl group, right? So it's off of a benzene ring. It's going to be around 2.3. There's a terminal alkyne, right? It's going to be right around 2.4 off that sp carbon. Here are bromines, chlorines, fluorine. So notice as we get more electronegative, right, we're going to be further, the chemical shift is going to be greater. Okay, so you can see that there. And then notice here that this is a hydrogen next to a carbon on an oxygen, and that's going to be at 3.3 as well. So we can use tables like this and look at our spectra to decide where these shifts are going to be. Here's the second part of this table from your book. We're going to see here if it's a carbon directly off a double bond, it's at 4.7. Now, look, if there's another R group there, if there's not a hydrogen, but another R group, it's 5.3. The hydrogen directly on an aryl is 7.3, and these give a really specific kind of messy pattern right around 7 that makes them very easy to identify. If you have a proton on a carbonyl, so for example, this would be an aldehyde, they're going to be anywhere from 9 to 10. This is a nitrogen on a amine. They're going to be 1.5 to 4. A hydrogen on an oxygen, like an alcohol group, is 2 to 5. An alcohol on an aryl is 4 to 7. And then a carboxylic acid is 10 to 12. Now, the ones shown in green here, they are sometimes harder to see. So that's why they've been highlighted in green. Now, to understand the characteristic chemical shift of each type of proton that I just showed you in the table, remember from section 17.3 that the effective magnetic field, which is BEF, which is shown right here, felt by a particular proton depends on the extent to which the proton is shielded by the surrounding electrons. Okay? If the extent of shielding for a proton is decreased, meaning the proton is deshielded, then the effective magnetic field increases. So let me put some words to that. So if the extent of shielding for a proton is decreased, right? Meaning that the proton is deshielded, then B effective increases, okay? And so an increase in B effective causes an increase in the energy separation between the alpha and beta states, right? And so we can see that here, okay? We get an increase in separation. So in turn, the proton will absorb a higher frequency photon and the chemical shift will increase. So if there's a larger separation, we get a bigger chemical shift, right? The chemical shift of a proton, basically, just to summarize, will increase as the extent of deshielding increases. Now, I have a great summary that I'm going to give you in class for this because I find that the terminology can get really confusing. So the more deshielded a proton is, okay, and now if something is deshielded, we're talking about this proton, that means it's got a more positive chemical shift, right? And it's farther to the left on the spectrum. Right? The more the signal is said to be shifted downfield. Okay, so conversely, the less deshielded the proton is, the more the signal is said to be upfield. Now, those terms downfield and upfield originate from older types of NMR, where the sample was irradiated with a fixed frequency, radio frequency, and the magnetic field was adjusted to make the delta E of the spin equal the energy of the photon. And so the more positive a proton's chemical shift, the stronger the magnetic field that was required, and vice versa. We don't use it that way anymore, and so it looks backwards when you look at it now. But just for some historical reasons, it's never changed. Now, there are two major factors that influence the extent to which a hydrogen nucleus is deshielded. One is inductive effects, and the other is magnetic anastrophe. And we're going to look at those right now. So, when we talk about inductive effects on a chemical shift, we can see that by comparing entries 2 and 12 in table 17.1. Now I stopped because I realized I didn't grab entry 12, even though I have a note here to do that. So I went back and I looked at it, and now it magically appeared. So notice in entry 2, which we're looking at right here, that's an sp3CH3, and you get a chemical shift at 0.9. In entry 12, the carbon is attached to a fluorine. And again, we're looking at the proton that's attached to that. And this fluorine is really super highly electronegative. The presence of that fluorine causes a substantial downfield shift. So we get a really big downfield shift from this, right, to 4.1. And a similar phenomena occurs with other highly electronegative atoms. So what we can say then is a proton signal is shifted downfield to a higher chemical shift value by nearby electronegative atoms. Now, this downfield shift occurs because the electronegative atoms are inductively electron withdrawing. So they remove the electron density from the nearby proton. Consequently, the shielding that those electrons provide is smaller, and the proton is deshielded. So the proton is said to be deshielded. Now, the extent of this inductive deshielding depends in part on the electronegativity of the nearby atom, as we've said. And so the extent of this inductive deshielding and the chemical shift depends on the electronegativity. So that's the first reason. The second reason that we is magnetic anastrophe. Now, that's the word anastrophe is derived from the Greek anos, which means unequal, and tropos, which means way. And it just refers to a characteristic that is directionally dependent. Okay, so basically what it does is it describes a magnetic field that is non-uniform and is responsible for large chemical shifts in aromatic compounds. So if we look, for example, in benzene, which is shown here, it's got a chemical shift of around 7.3. And what we can see here is there is a pi ring of electrons, and that pi ring of electrons occupies a space that looks like two donuts on either side of the ring. Because the electrons are charged particles, it forces the pi electrons to move in a circular parallel path. Moving along here, that external magnetic field that we're applying causes those electrons to move in this circular path, and that's called a ring current. And it creates this local magnetic field that's represented by the blue arrows. So notice that the proton or the hydrogen atoms in the benzene sit where that B local is produced by the ring current, and it's in the same direction as the external field here. And so the hydrogen nuclei of the benzene feel a greater total magnetic field and are de-shielded, which results in that larger chemical shift at 7.3. Now, we just don't see this in benzene. So we can also see this in vinylic hydrogen atoms. Now, or vinylic, I never say this correctly. So vinylic hydrogen atoms, right, which is, you've got two C's with a double bond and an H there. And so these are also de-shielded due to magnetic anastrophe. Though the pi electron density for a carbon-carbon double bond is not donut shaped, the pi electrons still undergo a circular motion on either side here. And this is either side of the molecular plane. And that again is caused by an increase in the local magnet, or the B effective, right? And so when we look at this, when we apply that external field, these electrons start to rotate around that double bond. So basically, we can sum up or generalize the things that we just talked about and say basically that magnetic anastrophe de-shields the nuclei of hydrogen atoms that are attached outside of an aromatic ring, like we saw in the previous slide, or, right, to an atom of a double bond, right? Like the carbon-carbon bond of an alkene, or even a carbonyl, right, for example, can exhibit this. That's why they have a larger value. So you might say, double bonds, right? I bet triple bonds would work in the same way. So we would expect, for example, maybe alkyne hydrogens to have high chemical shifts, but they don't. These chemical shifts tend to be relatively low, right around 2.4 ppm, which means generally they're much less shielded much less de-shielded than alkene hydrogens, right? And they're less de-shielded because the electron density of a triple bond has cylindrical symmetry around the bonding axis. So here's the bond here, and these move kind of parallel to that particular bond there. And as a result of this, that external field, when it's applied, tends to move in a path around the bonding axis. And so what happens is the alkyne proton lies where the B local opposes that external field, right? So there's our proton, right? That's where it's lying. And that results in a shielding effect, not a de-shielding effect. And so that's why we see such a lower parts per million shift. Now, you can predict approximate chemical shifts by basically looking to see if there are any electronegative atoms that are attached to the carbon attached to the proton, right? So the protons here are shown in red. And so one of the things that we know is that the effects that cause deshielding are essentially additive. So if we look at this, this is just like a CH3 group here next to an R group. We know that R just means rest of the molecule or CH3 compounds. Then if we look here, if we replace that R group with a chlorine, which is super electronegative, we see that the shift increases to 3.1, right? If we put a second chlorine on there, then all of a sudden now the shift is at 5.3. So what we're seeing here is the chemical shift increase with each additional chlorine atom that are attached to the carbon. A second useful trend for us when we're identifying shifts that relate to the molecular structure is to know that deshielding effects fall off very rapidly with distance, right? So in the case of ethylbenzene, which you can see here, notice how the chemical shift increases in our protons from 7.2 to 2.6 when the proton becomes one bond farther away from the aromatic ring. And then again, the proton decreases from 2.6 to 1.2 when there's another bond of separation. So we can see that these deshielding effects fall off very rapidly as distance increases. So how can we use the above trends to estimate the value of a chemical shift, right, that doesn't match the representative proton in the previous tables that we saw? So you can estimate this by adding. The problem here is that it doesn't always work out super well. And so the example that's given in the text specifically is starting out with this molecule, and they say, look, you're going to derive the effective substituent, the effect the substituent has on a chemical shift of a CH proton. So we're going to start here by taking 0.9, right? So we're going to start with 0.9 here. And then we're going to look at the substituent effects, right? And then we're going to add 2.2 for chlorine. And then we're going to add 1.4 for this aryl group here. And so when you do this, you can see that this would be around 4.5. One of the things to be aware of is that when you look back at table 17.2, what you're going to see is that the substituent effects are approximately 20% of the listed values when one additional bond separates the substituent from the carbon-hydrogen proton. Now, you can use this, and this does somewhat agree. So this is predicted here. And so what we do see is about a 4.6 ppm shift there when we look at that. Now, it does go through and looks at those substituent effects, And so we can look at the substituent effects and see, right? So if we look at this, it's the shift of the substituent, which is shown in red, to CH3 minus the shift of the RCH3. So basically, this is what I was inferring in the previous slide, is that we can say, look, we can take 1.7 parts per million, which is the shift that we see when there's a C, double bond C here, and subtract 0.9. And so we can say, oh, hey, look, this part in red, the substituent effect there is 0.8. This is okay, and if you want to use it, that's fine. What I find that students just do better with is understanding that fluorine, your halogens are going to have a greater shift than other hydrogens, for example. So if something's attached to a halogen, it'll have a greater shift. Now, when we talk about chemical shifts, and we've said chemical shift a lot. Chemical shift, and I mentioned previously, it's represented with a lowercase delta, and it's just a measure of the extent to which the signal's frequency differs from that reference compound. When we talk about a reference compound, it's in parts per million, and so if you're curious as to where that parts per million comes from, right, it takes the frequencies of the sample and subtracts the frequency of the reference compound, which is TMS, over the frequency of the operation, or the operating frequency. And it multiplies it by 10 to the 6th. And that 10 to the 6th is where we get the parts per million from. Now, one of the nice things about NMR spectroscopy is that a proton's chemical shift is the same regardless of the NMR instrument used to make it. So because we have the TMSs used as the standard, that's what we see there. Now, when we talk about making up our samples, we generally try to use deuterated solvents. Now, deuterated solvents, some ones that are pretty commonly used are deuterochloroform, which is CdCl3, right? Or deuterium oxide, which is D2O, or deuterated acetone, which is CD3COCD3. The reason is this is proton NMR, and if we were to use something like water, the peak from the protons in the water, because the solvent has so much more of the sample volume than the actual sample, would just be huge. So this helps us see our sample solvents, and it doesn't require quite as much sample. So we only need about 5 milligrams, which is really helpful because a lot of times we're dealing with really small percentages of sample.